Howdy and welcome back. Let's get started. So our first topic here is going to be handling non-local errors at runtime. So just to remind you, runtime errors are going to be errors that are going to be found by checks made during a running program. So we've gone through the compilation process. We successfully converted our program into machine instructions that a computer is able to understand, and we've launched it up and now we're executing it. Runtime errors will be errors that are now detected as our program is running by either the computer, so hardware, and or the operating system, a library. In this case, maybe the standard library facilities that we've used up until this point, like standard library vector, which could tell us if we were outside the range of acceptable elements within its storage, uh, standard library string, etc. And then also we'll get into a brief discussion here on user code. So runtime errors detected by user code. Errors obviously disrupt the normal flow of our program's execution. We can find these errors through various checks made during a running program. Local runtime errors are pretty easy to resolve. For instance, let's say we've started up our program and we were expecting 2 command line arguments, but only received 1. It's very easy and appropriate to deal with that error in a local manner and simply go ahead and type out some sort of usage to the user and terminate the program. Or maybe we've received the correct number of arguments and we're still in main, and one of those arguments was a file and we were unable to open that file. So maybe at this point we could easily say, hey, I wasn't able to open your file, and terminate the program at that point. So these local runtime errors are very easy to handle. A lot of times there's a well-defined way to go about handling them. This question becomes a little bit more difficult when we start focusing on non-local errors that arise during runtime. So to give you an example of this, consider this code. I have main.cc over here on your left. All that is happening in here is we're calling a user-defined function area of a rectangle. And then we're going to go ahead and store the computer result in a variable named area and output that to standard output. We can stay here following best conventions. The declaration for this function is provided in a utilities.h header file. With the name simply communicating that, I guess these will be utilities that I'll be using within the program that I'm writing. This could have been my math functions, whatever, but obviously a name that communicates which declarations are being stored within it. Finally, if we look at the corresponding source file, by convention, it's the same name as the header file, but with a different extension, .cc or .cpp, depending on your preference. The core style guide does suggest the use of .cc. Here, we go ahead and define what it is this name block of code will do. An area rectangle is simply going to return the width multiplied by the height, just the computation of what defines an area of this particular geometric shape. So if we just look at this, we might go, okay, this is probably a sufficient information or implementation. And then you begin thinking and you go, well, what if, like a negative value gets passed? So negative 10 times 10. Negative 100 is not going to be a valid measure of area. Area can't be negative. It has to be some sort of positive value. So what are some ways to handle with these sorts of errors that can arise during the execution of our program? So one way to go about this is to go ahead and have the caller deal with the error. So we could say that, hey, I'm in the implementation, I'm not going to provide any sort of error checking to ensure that, say, my width and my height values are both positive and therefore valid. So instead, if the case comes around that a negative value is passed into this function and we compute a negative error, I'm going to say that the caller, so the person who called my function, will have to deal with that. So they're going to have to go ahead and go, okay, well, hey, if the area I get back is less than 0, well, something's astray and I need to figure out what it is and properly handle that error in this case. So that's one way of going about this. The other way is going to have the callee to deal with the errors. And this would be the actual functions that's being invoked is that, hey, if the parameters don't look quite right, I'm going to go ahead and handle that. For instance, here, we could go ahead and launch up our function. We could calculate the area and we could simply go, okay, well, if the area is less than 0, we know that's impossible. We'll just go ahead and assign area 0 and return that value. Otherwise, if we have a valid computation of area, we could go ahead and return that computed value. Now, here's where things get a little bit tricky. Note that this error was never acknowledged to the person using the area rectangle function. So the question could become, well, why did this function compute a negative area? Where did this happen in the code? For instance, you could assume that these are variables and at somewhere in maybe the program where we went ahead and assigned their values, maybe some sort of incorrect computation was made, maybe an incorrect measurement that gave them the wrong starting values, and those values ultimately got passed to our function. We wouldn't know that this even happened because we'd be receiving a negative area measurement back, and we would just, probably assume that the value is the right and the area that was computed by this was right. But that's probably not what we'd like to happen. We'd like to at least have our attention drawn to the fact that, hey, an error happened during the execution of this function, and maybe allow the user some way to go about handling that. So, handling non-local errors at runtime. The previous means of error reporting are not general. Consider that most of the time we can't change a function that handles an error in a way we don't like. For instance, looking back here, let's say that, maybe this is code I wrote that I provided you with. And I'm saying, okay, you can't change the definition, you have to use this. This will happen frequently whenever you're interacting with, say, library code. You won't have access to change up the definition to your liking. You're going to kind of have to deal with what was dealt to you. So the question becomes, okay, well, if we can't change a function that handles errors in a way we don't like, well, what options do we have? So to just kind of reinforce this, the author of the standard libraries vector can detect runtime errors. For instance, maybe you're trying to access an element that's outside the bounds of that vector. However, she or he has no idea what you would like to do in this scenario that the user is attempting to interact with something that doesn't exist. Likewise, the user of the standard library vector probably knows what they'd like to do when such errors arise. However, she or he cannot detect them because, again, the error is not arising in their code. It's arising in the code that they're interacting with. And if this wasn't the case, otherwise he or she would find them in his own code, not left for the library to find. So we need some means of reporting errors in a general way, which would kind of separate these concerns. What we want to happen is the ability to separate out the actual error reporting from how we go about the error handling. For instance, the author of the standard library vector could go ahead and tell us somehow, report that an error arose, and then ideally, we'd like to be able to receive that report and determine how we'd like to go about resolving that. So we need some sort of separation of concerns here. And what we'll see moving into the next video in this lesson is that exceptions do just this.